Hello all. As I told you in my class that it is not possible for me right now to demonstrate a physical version of the motor, and therefore I have no other way out rather than filming a short video from which you can get a little bit of idea how we should like what a real motor look like. Of course, this is the outside. Here, please understand, we are taking the side view. This portion, this long end is called the motor shaft. The rear end cover is removed. This is a damaged motor for demonstration purpose only. So here you can understand that shaft is placed along the axis of the cylinder. If I open this one, then I will get it more clearly like this. This is the part that I'm holding. This is called the rotor. This is placed in center of this hollow cylinder called stator. This is a hollow cylinder, you can see. Now this hollow cylinder, the axis of this hollow cylinder must be like it must be collinear with your axis of the rotor, right? Here you can see this is the stator winding. Let me see, I am recovering, so I am a little low in my energy. Here you can see this is our stator winding, right? As I was telling that these are the conductors. Hope you can see these are the conductors, right? And this part is called slot. Now please try to understand when we will think about calculating the effective iron area for calculation of flux for a given flux density. Then, as you know, for a cylinder the volume is the area is pi dl. So in that pi dl part, the L should be considered only from this to this, right? From here to here, not the entire axis length or anything. Only the length of the axial length of the stator must be considered. And for diameter purpose, we must only consider the inner diameter of this cylinder. This cylinder I am referring the inner dia of this cylinder, right? And also I do not know whether you can understand it clearly or not. Here if you see these slots, this iron this is called the slot teeth. These are like a bit these slot teeth are bit kind of like not straight, rather they are bit tilted. You can get a better idea if I place it for our rotor. You can see that rotor is also not exactly in straight line, rather it's bit tilted. Why this tilting is there? This is to avoid the kind of like uh, some to avoid adverse effects of harmonic torque and ensure our machine performance. How these torques are getting generated and how things happen in a real machine, that we will discuss later on during our analysis. In addition, as you know that every iron part of the machine must be laminated, especially when the part is subjected to alternating flux. So if you ask me, sir, where is the lamination or how we should laminate here in this machine? So please look at this. Let me try to zoom it. Oh, it got black. Now that's perfect. Now I hope you can see it. Here you can see these are the lamination. So how we should laminate our machine part? The lamination is done to ensure that your machine actually we can say that we should laminate our machine stator structure perpendicular to its axis, right? As you know, to reduce eddy current, how you should laminate parallel to flux path. So from that statement, we can also get some idea how flux will be like generated and circulated in this path. Actually, flux will be generated perpendicular to the axis. Which axis I am talking about? About the hollow cylinder axis. And when I will place the rotor inside this hollow cylinder, that will also be considered the same axis, right? And here I was talking about varnish. So you see these as if these are giving you an impression. They are just let me hold for a few seconds so you get a clear idea. Yeah, so you see these conductors looking like they are bare copper conductor, but they are not bare copper conductor. Actually these conductors are actually varnish insulated, and therefore even if you place them like adjacent to each other, they are not getting short circuited, or they are actually representing separate individual turns of your coil. So now if we have to understand where is the coil start and coil end, you may see that, say this is one end of my coil, right? And how, see this is a two layer machine, as I was telling last day. This is a two layer machine. One end, remember, whenever we have two layer machine, one end of the coil must be placed at the top layer, the other end must be placed at the bottom layer. This will ensure the evenness of the magnetic circuit. Secondly, this will also ensure that you have a mechanical ruggedness of the entire structure, because if you place all the coils, say a certain number of coils in the top layer, then there is a chance that they may get dislocated when machine is in run or machine is in vibration. But when you have the coils, then there is a chance that you place it in this manner, that you have top layer and then it goes to the bottom layer, right? You can see it from here, it goes to the bottom layer, right? This is a 4-pole machine. Now here it takes it is there, and now it goes to the bottom layer. So what does that bottom layer means? That bottom layer means when you have this coil, one end of the coil is placed in the like it is in the bottom layer, so you get better mechanical strength. And in terms of magnetic evenness of the magnetic circuit, you can understand, if we place the coils, suppose we place certain coil in the top layer and another few coils in the bottom layer, then what would happen? The coils placed in the top layer, they are exposed to the air gap, and they will experience a higher amount of leakage reactance. Sorry, not higher amount, rather they will experience a flux. Not let me not bring the leakage reactance directly here. That is a like complicated calculation. Let me tell you only at this moment you can understand that if you place some coils in the top layer, then with different amount of exposure to air, they will be subjected to path of different magnetic reluctance. Because if you place coils in the bottom layer, entirely in the bottom layer, then that coil will be subjected to, mostly cheaply it will find it flux path through iron. And if you place coil entirely in the top layer, it will find its flux path through iron and air, and therefore their like magnetic circuit will become uneven, and that will create an unbalance in the end. In addition, this is a three-phase structure. Please note that in case of three-phase, in order to ensure that evenness of the winding, we must need number of slots that is an integral multiple of the number of phases. So if you have 3, it must be an integral multiple of 3. However, there is no certainty that if you try to find out the number of slot per pole per phase, that will also become an integer. It can become a fraction. We will discuss that later. In addition, what we mean by the coil pitch, this is one end of the coil, and like here you can see, although the other end is placed in the bottom layer, but we can calculate that coil pitch is like, this is 1 slot, 2 slot, 3 slot, 4 slot, 5, around 6 slots are here. So basically, if we count here, you will see this is a 24 slot machine. So 24 slot means if we start from 1, then we are having actually 24 slots. So in general, if you place one coil, so 24 slots roughly speaking, what should be individual coil pitch? You divide 24 by 4, then you will get some idea. But here what is happening, these 24 slots is divided, and in 4, I think it's a 4-pole structure. I have to check once, but see what is happening here. The slots are placed in such a manner that this phase goes in this way, right? So what we are experiencing, that if I have to count the slot pitch of the coil, then 1, 2, 3, 4, 5, 6. Supposedly here the coil enter its or find its slot for bottom layer. What I am talking about, the slot is not this one is teeth. This one is slot where your coils are placed. So don't get confused between the teeth and the slots. Slots are the group area, the group part where your coils are actually placed, right? So I think most of the things I have demonstrated. These like solid, heavy wires are actually indicating they are the terminal wires that are connected to this top part. Actually this is a delta connected machine, so we are having 3 terminals getting out of our machine. Had it been a star connected machine, we could have we would have 6 terminals, sorry, not 6, rather 4 terminals for our stator would be available here. In addition, now coming to the rotor part, this is our rotor. Although this is an induction machine rotor, but in case of synchronous machine rotor also we can have this kind of cylindrical structure. And when we will rotate this cylindrical structure, what will happen actually? Let me explain you. After placing this, yeah, now see what I was trying to tell you. When this machine is here, now suppose you have some coils are wound around your rotor. Although here rotor structure is different, but let us consider rotor is carrying some current carrying conductors. Now when you make your rotor rotate, then what would happen? Then your the stator winding, which is in the inner periphery of your hollow cylinder, which we call the stator structure, they will experience time varying flux, and since they will experience time varying flux, therefore EMF will be induced. Now what I was trying to tell you, suppose you have one coil placed here and here. Say I'm just giving you a very crude example, one phase coil placing here and here. So when they will experience peak flux variation after 120 degree of space traversal, coil that is placed here will experience similar flux variation. And further you have to, so which 120 degree I am talking about? I am talking about this 120 degree, right? This 120 degree I am talking about. When this experience 120 degree, then you have that flux variation. So here in this process you get that if you place the coils in a proper judicious manner, then they will be able to experience different like they will reach their peak at different time instants, and that will be governed by that 120 degree space angle. Who will determine the time gap between say when this coil will reach peak value and when the coil placed here will reach its peak value. It will be governed by this angular speed of this one. And here I am rotating using my hand, but in general we use some kind of prime mover. In your machine lab you see in synchronous machine we have a DC motor mechanically coupled with its axis, its shaft, and that is giving us the rotational speed, and that is called the prime mover. So if we increase the speed of the prime mover within a very short time, this will reach from here to here. So basically for 120 degree angle electrical angle traversal, it all depends on the speed of rotation or this angular rotation, this like rotation of your shaft or rotation of your rotor. So the frequency of alteration, frequency of generation, all these things will be governed by the speed of the mechanical alternator. Last but not the least, before I conclude this video, let me just tell you a few things that you are going to study in this process. What are they? So first of all, we have to understand that when we are having this kind of electromagnet, even we place them on our rotor evenly, if we place them, still can that rotor give us a very even kind of MMF distribution? Because if your MMF distribution produced by your rotor is not a very sinusoidal one, what you can expect? Forget about mathematics. From our intuition we can say that whatever induced EMF we will have, that will not also be very smooth and sinusoid in nature. That could become contaminated with higher order harmonics, because the induced EMF, sorry, the MMF produced by the rotor is not a very sinusoidal one. So we will teach you that how we could make the MMF produced by rotor sinusoidal. Then we will teach you, even if we don't have the much control over the rotor, because see, all these are real engineering process, and even if we wish for something, we cannot always get those things. It is not your grading system that you wish for EX and if you give a little bit of effort you may get it. It's not like that simple. It is an engineering process. You have to it really like very taxing process. So when you have this one, then what you will get? You will get that your flux, even the flux, you cannot have much control over the flux pattern, but still how we can do some modification of the stator side, that we can get a smooth EMF induced across my stator winding. And lastly, that is very, very important for us, we are generating three-phase. Fine, we learn how to place the coil. Now suppose you connect some load, because here by rotating this one you are generating some EMF in the machine, but that EMF, when you will connect a load, these coils will start carrying current, and when current will flow through this stator winding, by virtue of Lenz law and by virtue of energy conservation of electrical energy, what conservation of energy, not electrical, mechanical energy is also a part, what you will have there, the whole process will get a kind of obstruction, or kind of like the current that is flowing through your stator winding because of this connected load will try to oppose its varicose. Now if you look at or try to think, it is only about, you have to feel and think, nothing rocket science we are discussing here, nothing very critical like a quantum mechanics kind of things we are discussing. It's very macro, very uh, crude things we are discussing. Just you need to be a little bit of sensitivity is required. So when you are trying to feel that one, that how your stator coils will be reacting when it is carrying current to oppose its varicose, it will find there is a two reasons are responsible for generation of the EMF. One is what? See, if you can reduce this rotational speed of this shaft, then you can effectively change the rate of change of flux, because even if you allow same current flowing through your rotor and producing same amount of electromagnet, same magnetic field strength, but if you can reduce this rotational speed, then you can reduce or can curb that ddt, and in that process you can reduce the EMF induced in the stator coil, and in that process you can reduce the current flowing through the stator winding. On the other hand, what you can do, you can produce, just like a transformer, you can produce a demagnetizing MMF that tries to oppose the original field produced by your field winding. So in this two way, your stator winding current can try to counterbalance. That's all for this video, and here is the machine nameplate. It's getting a bit, yeah. So here it is a two-pole machine, and this is, you can see it's National Electrical Instruments, manufactured by National Electrical Instruments. The voltage rating is 440 volt, and remaining things I cannot, yeah. The speed is many things are not very clear, like what was there initially, but this 1410 perhaps denoting the amount of like if you load the machine fully, I suppose then you can get this much speed. Those things we will discuss later. And this 3.6 perhaps indicating the full load current, and these I'm not very sure, so let us not do this kind of guessing. Rather, let me conclude this video here.